right, guys, we are back. Okay, so let's go ahead and let's do a quick little just summary, so to speak. So, mind you, this is actually our third day on this Operation Jackpot. We went ahead, we answered some pretty critical questions. Remember, we talked about, hey, chaotic, that's actually pseudo random, which is it basically it comes down to a physics problem. Then we had the quantum effect, which is truly random. So that means even if you have all the variables, you don't necessarily know the outcome. Okay, so it seems to be lingering and basically playing like a seesaw, so to speak, on those two things. We talked about the statistics. We already know, hey, to get all the numbers, five numbers plus the Powerball is going to be basically 1 in 300 million chance to win. We talked about some of the people who are pretty significant in the field because they've won the lottery multiple times, and it seems to me that they obviously have a strategy. And when we came back to day two, we talked about, hey, what's going to be our strategy, right? So we got some numbers down. We're like, hey, it costs $2 for a line. We probably want 5 to 6 lines. We're going to play once a week, so we're looking about $12 for 3 months, and that's basically going to be, it's basically $150 project overall. Okay, hopefully we win some. I mean, if I can just break even, I'd be happy. If we win the lottery, heck, we might get some better hardware on our end. But nonetheless, things to review. I know I mentioned that, hey, with all this data analytics stuff, we're going to use this as a great opportunity to maybe learn some Python, maybe go ahead. I talked about Python Panda because we're not going to use too much data. I know that we can probably even get away with we could probably get away with it with an Excel sheet. But I was looking into things such as like MySQL, databases nonetheless. So we can type that in right now, MySQL. Okay. But yeah, we want to use this project to learn as well, get new concepts, get new ideas, look at some new tools. And we basically broke down our strategies. We said since we're having 5 to 6 lines, each line is going to be representative of a strategy. So the first one, we actually went with the quick pick. I know. You guys are like, hey, but Richard Lustig said that don't use a quick pick your own numbers. Well, we're going to go ahead and compare these six strategies and see how they do within that time span of the 3 months. So the first strategy, and I think most people pick this strategy. I know I played it once or twice before. Usually I don't pick numbers. Usually I go with quick pick. This whole idea of pick your own numbers, stick the same numbers, use a balanced set of numbers. Believe it or not, it's new information for me. And I'm looking at it differently. This is literally the first time, not the first time, but the second day was the first time I sat down and I actually thought about, hey, let's take this approach, right? The whole idea of picking your own numbers, stick with the same numbers, use a balanced set of numbers, play consistently, buy more tickets. No, we're not going to join a lottery pool. I already established that. But nonetheless, manage your money wisely, so on and so forth. And for one reason or another, of course, my mouse would give up right in the middle. I might need to change the batteries. Oh, there it goes. Okay. Let's go. Let's see. Mind you, this is a long. I try to keep it less than an hour. Maybe I should shorten it down. But this right here, guys, I'm literally just explaining my thought process. Like my what I would basically do behind the screen, so to speak, like when no one's watching. This is kind of what I do when I'm looking at a subject. So I'm recording for my purposes. Hopefully you find this helpful. I know some people watch the videos. If you guys see something I don't see, please chime in. Let's go ahead. We'll talk about it. Never mind the spelling mistakes that happens to me often. Yeah, just we'll get into this. So we, out of the people that we mentioned, okay, we mentioned that Richard's method we can definitely use. Stefan's method, I wish they would have said, I was thinking the other day, and this is a cool thing about doing videos like this, is that it sticks and you get to learn more of the material. I was thinking a little bit more about the other day, and obviously we're not going to have $300 million to cover each and every single number. Okay, but I was interested in regards to how he found all the combinations. In other words, how he found what numbers Okay, and it's kind of like a brute force. It's kind of like, what did he do? Did he go one 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 one, and then two 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 two, and then it just started changing like each individual thing, So I kind of got interested, like, hey, what mathematical equation was he using? But nonetheless, his method we can't really use besides the idea of, hey, cover your bases. Okay, and we'll try to cover our bases as best as we can, but just looking at the numbers, it's that's literally why it's 1 in 300 million. We talked about Mohammed. I really liked Mohammed. His strategy. He had a number pattern analysis. And when I asked ChatGPT about his number pattern analysis, it was more so in regards to, hey, look at the actual definition. You have arithmetic, okay, which can be minus, addition, subtraction. You have geometric sequences, which is more so like, I'm not too sure exactly what that was. I gotta look that up. Geometric sequence. Excuse me. That was more divide and multiply. You had a mod, which I know that's a way of counting. It's like 3 1 2 0, 3 1 2 0 1 2 0. I gotta look a little bit more into mod because I know mathematicians know that a heck of a lot better than I do. It's just and I think this is what it is. So if you have like a mod 7, that means you're going 1 2 3 4 5 6 7, and then you're counting again 1 2 3 4 5 6 7, and then it starts all over again 1 2 3 4 5 6 7. So I do think that that's exactly what a mod is, um, and we can double check that. But nonetheless, we got into some hairier things with regards to chaos and randomness and number sequences and logistic maps. And I was just like, whoa, whoa, whoa. This is something that we can probably test later on, but I just want to go through all the strategies first. And nonetheless, we technically, we've picked our numbers, right? Um, with this is where we're going to need some panda, and we're actually going to have to go ahead and get the numbers from the lottery, when we don't have those numbers yet. And nonetheless, I want to keep moving forward with the actual strategies that we have. Okay, so we talked about Mohammed. The next thing we're going to talk about is Joseph. Okay, so let's go ahead and talk about Joseph and let's see what he was doing. So this is going to be number 4. Okay, number 4. And this was Joseph. And this is number distribution. So I want to go ahead and find out, hey, what exactly is number distribution? So we're going to go to ChatGPT. We're going to ask, um, I'm new to this idea of number distribution. Can you please explain to me the concept? Okay. So let's see what ChatGPT has to say. Let's go ahead. I want to make this bigger so I can always bring this back. But nonetheless, let's see. Okay, so what is number distribution? In the context of mathematics and statistics, number distribution refers to how numbers are spread out or arranged across a range or set. It shows where the numbers are located in relation to each other and how frequently certain values appear. For example, if you roll a fair die multiple times, the numbers you get on the die will have a distribution. Some numbers may appear more frequently than others, and some may not appear at all during certain trials. Uh, Uniform distribution, every number in the range has the same probability of occurring. Okay. For example, when you roll a fair die, the number 1 through 6 have equal chances of appearing, so the distribution is uniform. All right. Normal distribution or Gaussian distribution is a bell-shaped curve where most of certain clusters where where most of the numbers cluster around a central value, a mean. Okay. Fewer numbers appear as you move away. For example, people's heights are often normally distributed. Most people are around an average height, with fewer people being much taller or shorter. Okay, this is something I can deal with. We've all looked at the bell-shaped curve, where it just comes to the mean, and then you have your outliers. So the number normal distribution, I'm just thinking about, hey, what's the most common number? Or actually, in this case, bell shape where the most of the numbers cluster around the mean. So it would just depend on the numbers, So the normal distribute, because we're under the impression, at least I am, at this point in time, I'm under the impression that you're going to have numbers 1 through 69. It doesn't seem to go ahead and repeat. So you basically have a 70, I guess, depending on how you count that, but 1 through 69. What you have, 1 in 70 chance of picking the right number. And I guess that chance goes ahead and decreases as the numbers are picked. But nonetheless, skewed distribution. Okay, so uniform distribution. Okay, you have normal distribution, and you have a skewed distribution. Okay, so this is, if the numbers are not symmetrically distributed and lean toward one end, it's called a skewed distribution. Positive skew, the majority of numbers are small, but they are very large values. Negative skew, the majority of numbers are large, but they are very small. Wait, what? The majority of numbers are large, but there are a few very small values. That's interesting. Okay, I got to look at this. So the majority of numbers are small, but they are a few very large numbers. That's so interesting. I don't know how they came up with that definition. Positive skew, the majority of numbers are small. Okay, so that would be something like one, two, three, four, five. But there are a few very large values. So that would be something like 36, 55. So I guess that's the idea of positive skew. And then negative skew, the majority of numbers are large. So that would be like 55, 60, 67. Okay. But there are a very few small numbers. So nonetheless, okay, so I guess we're literally getting into what would be definitions. And because they're definitions, this is something that we would want to go ahead, copy, and note, so to speak. Binomial distribution. This is often used in situations with two possible outcomes, like yes or no, true or false, repeated multiple times. For example, flipping a coin several times and counting how many heads appear follows a binomial distribution. Okay. I mean, that's pretty simple. That's just literally discrete. It's literally a zero or one, in other terms. Let's get some examples. So, test scores. When you look at a group of students score on a test, most students might score around the middle, with fewer students scoring very high or very low. So, when I look at test scores, that should be a normal distribution. I'm thinking bell curve. Income distribution. In many countries, most people earn a median income, with fewer people earning extremely high or extremely. So that would be another normal distribution. I'm thinking bell curve, because I'm just thinking of the mean. Measures used to understand distribution. Mean, the average value of the numbers. Okay. Median, the middle value when the numbers are ordered. Mode, the number that appears most frequent. Variance and standard deviation. These measure how spread out the numbers are from the average. Okay. Why is number distribution important? Understanding number distribution helps in making predictions, comparing data, and drawing conclusions in many fields, such as economics, science, and social studies. For instance, if you know the distribution of people's incomes in a city, you can predict the average income. How is that? If you know the distribution of people's incomes in a city, you can predict the average income. I mean, wouldn't you just look at the mean? So I'm kind of curious, if you know the distribution of people's income in a city, you can predict the average income. Nope, still don't get it. If you know the distribution of heights in a population, you can determine what percentage of people will be taller or shorter than a certain height. Okay, that kind of makes sense. I mean, I'm telling you, it all comes back to the mean. In summary, number distribution helps us understand how data is spread across a range and provides valuable insights into the trends, patterns, and behaviors. Does that help clarify things? It does. It really does. So we're going to literally just go ahead and from this, I'm going to take these ideas. Okay. So we have the type of number distribution. So I'm going to go ahead and literally just copy and paste this. So I'm going to take this, we're going to copy, we're going to go back to our notes. That way I have less typing to do. So remember, his goal was number distribution, and he's saying it was not truly random. So let's go ahead and clean this up here. Types of number distribution. So we had uniform. Okay. Let's see. Uniform. Okay. So it should be something like this. Here, here. Skewed distribution. Skewed distribution. Remember, we had that idea that there's basically a positive skew and a negative skew. So we're going to have to get really comfortable um, with these terminologies so we can actually start looking to see, hey, what's the normal distribution? What's the skewed distribution? What is there uniform distribution? And then I really like this idea. I mean, this is literally like fifth grade math, in the sense of, hey, look at the mean, median, mode, variance, standard deviation. I have a hard time with that though, if I'm going to be honest with you. Um, I don't know. Okay, so we had those notes there. I don't know what they mean by standard deviation now. Explain to me the idea of standard deviation. Come on, ChatGPT, explain it to me. Explain to me the idea of standard deviation. Great question. Standard deviation is a key concept in statistics that measures the spread or dispersion of a set of data points around the mean. In simpler terms, it tells us how spread out the numbers in a data set are. Here's a step-by-step explanation. Okay, so hopefully by the end of this video, we learned what a standard deviation is. Standard deviation is a number that describes how much the individual data points in a set differ from the mean average of that set. Okay, so a low standard deviation means that the numbers are close to the mean, and a high standard deviation means that the numbers are more spread out. Okay, that makes sense. If the mean is 10. Okay, if the mean is 10 and you have a low standard deviation, that means that you're more likely going to be around the realm of like 9, 8, or 7. And then if you have a high standard deviation, the numbers might be around, let's say, like 18, 19, 20. The steps to calculate the standard deviation. Ooh, yay, more formulas. Okay, so the steps to calculate standard deviation. Let's break it down with an example. I like examples. Suppose we have the following 5 test scores. Okay, you have 10, 12, 15, 18, 20. Okay, the mean is simple. Like, I get that. I mean, I'm looking at it right now. It's right in front of me. But the mean, you would add them, divided by 5. Okay, you get 75 divided by 5 is 15. So the mean's 15. Okay, so far so good. Okay, no troublesome math now. Let's see if we can guess the mode. The mode, I'll be honest with you, the mode, I don't see the mode. Looks like they're all the mode. The mean, what would be the mean in that case? Um, would it be 15? I'd laugh if it's 15. Um, find a difference from the mean. Well, hold on. Well, like, hold on. Go ahead. We're going to take this. Let's do this. We're going to put a bookmark here. We're going to duplicate this. And let's start with what we know. I feel like that's always good. Mean, mode. What was it? It was mean, mode, and median. Median, solve. All right. Let's find the mean, mode, median, and set numbers. Okay, so the mean was pretty easy. That was 15. The mode, there was no mode. I got one right. And the median, funny enough, it's 15. The median is the middle number when the data set is ordered. Since the data is already increasing in order, the middle value is the third. Oh, okay. So 15 was the median, but it wasn't. I got the answer right, so to speak, but I didn't get it right because of my thought process, or why I thought it would be 15. I actually I got it right out of dumb luck. Um, I was thinking, yeah, okay. So the median is the middle number when the data is ordered. Since the data is already in increasing order, the middle value is the third. Okay. All right. So I mean, hey, we can mess with that. We know what mean is. We know what mode is. We know what the median is. Let's go back to this idea of the standard deviation because we were trying to calculate the standard deviation. Find the differences from the mean. Okay. Each number in the set, subtract the mean and get the difference. That's that's all we have to do. Okay. So it looks like it's 10 minus 15, negative 5, 12 minus 5, negative 3, 15 minus 15 is 0. Um, 18, 18 minus 15 is 3. 20 minus 15 is 5. Square the differences. Okay. So since we're going to square it, and even if it's a negative number, it's always going to be positive. Next, square each of those differences to get rid of any negative signs, since we are concerned with how far each value is from the mean, not whether it's above or below. Okay, so you're squaring them. Find a variance. I mean, how do you find the variance? You find the variance literally by taking the mean. 25, 9, 0, 9, 25. That's so weird. The variance is the average of the squared differences. Okay. Take the square root of the variance. Oh, wow. Finally, to get to the standard deviation, we take the square root of the variance. So what the heck does 3.69 mean? So the standard deviation of the test score is approximately 3.69. ChatGPT knows what I'm going to ask. Interpreting the standard deviation. Low standard deviation. If the standard deviation is small, okay, but small is relative, it means that the numbers are close to the mean and there's very little variability. High standard, if the standard deviation is large, it means that the numbers are spread out over a wider range and there's more variability. Okay, so ideally, in our case, we would want a low standard deviation. I'm just thinking off the top of my head. It's like the low standard deviation would allow you to go ahead and pick closer and closer numbers. Okay. Low standard deviation. If your test scores are 18, 19, 20, 21, 22, the numbers are all close to the mean 20 and the standard deviation would be small. If your test scores are 5, 10, 25, 30, 50, the numbers are spread out far from the mean and the standard deviation would be larger. Why is the standard deviation useful? Okay, it accesses consistency. Okay, so that's what we want to see, right? We want to see if we can start to pick patterns within the lottery. That's obviously what we want to do. Risk assessment in finance, standard deviation is used to measure the risk or volatility of an investment. Oh, that's interesting. I never knew that. But I mean, what would be the input? I mean, I think we've all played around with stocks. With either, I mean, Bitcoin or anything along those lines. Webull, Robinhood, all that good stuff. Risk assessment in finance, standard deviation is used to measure the risk of volatility of an investment. A high standard deviation indicates high risk. That's so strange though. But I mean, what's the input? What would be the input, guys? So if the standard deviation is a reflection of the risk assessment, what are you putting into the equation? Um, that's kind of strange. I don't know. Something to look into, but nonetheless, lottery, right? Quality control in manufacturing, companies use standard deviations to measure the consistency of their products. Yeah, that's a good way. Standard deviation between a standard deviation versus variance. Variance is the average squared deviation from the mean. However, it's not in the same units as the original data because the differences are squared. For example, if you're measuring in meters, variance would be in meters squared. I don't think that applies to us. Standard deviation, on the other hand, is in the same units as the original data because it's the square root of the variance. This makes it easier to interpret. Okay, so it's just saying like, hey, your variance, if you're taking measurements of a volume of something or the distance of something, that it would be meters squared. Recap: standard deviation measures how the spread of numbers in a data set are from the mean. A low standard deviation, okay, it is useful in many areas like statistics, finance. Okay, so what I got from this, okay, guys, was basically how to calculate the standard deviation. Okay, so we know that, and this time we can type it. So we know, okay, we know. Let's go back to this. We know there is high. We know there is high standard deviation and low standard deviation. Okay, generally speaking, with high standard deviation, okay, with high standard deviation, numbers are spread out. Low standard deviation, numbers are closer together. Okay. And how do we calculate the? Okay, so it looks like in order to calculate the, okay, to calculate standard deviation, what we're going to do here is quite simple. Okay, we're going to basically take the mean. No, we're going to find the mean. So step 1, find the mean. Okay, step 2, subtract the mean. Subtract the mean. Okay. Step 3 is the variance. Variance basically means square the result. And then step 4 would actually be to go ahead and variance, basically square the result. After that, we're going to go ahead and take the mean of the variance, basically square the result. Okay, let's put it like this here. Variance actually should be here. All right, we're basically going to square the result. We're going to take the mean of the variance, and then we're going to go ahead. Once we take the mean of the variance, we're going to take the square root. Okay, square root of the variance. This is why I like to use ChatGPT for obvious reasons, as you guys can see. But nonetheless, let's go ahead and ask ChatGPT. Hey, ChatGPT. Hey, ChatGPT. Give me a quick problem so I can solve the standard deviation. All right, let's make sure that we know, hey, what we're doing is right. Cool. And this is what they gave us here. They gave us 23, 27, 30, 35, 40. Okay, so hopefully you guys saw the notes. If not, let me put it here to the side. So we're going to find the mean. So let's get our handy dandy calculator. All right, guys, you guys know my video cuts off at the 30-minute mark, so we're halfway there. Let's get through this here. So we're basically going ahead and calculating the standard deviation. So it should be 23 plus 27 plus 30 plus 35 plus 40. Okay, we get 155. Okay, so we get 155 Perfect. So we get 155. Now we're going to take that 155 and divide by 5. So now we get 31. So the 31 is the mean. Okay, so that means we're going to go ahead and take 23. I got my little pencil on the side here. 23 minus 31. Okay, let's just go ahead and multiply now. Actually, I don't want to confuse you guys or confuse me. So far we just got in the mean, right? We added all of them together. We got 155. We divided by 5. We got 31. What I'm going to do is I'm going to do this. I'm going to take 31 minus 23 minus 31 because that's the first number. I'm going to take 8, okay, and I'm going to multiply. 8 times 8 is 64. So we're looking at 64. So, and then we're going to go ahead and take 27. So 27 minus 31, okay, we're going to go ahead and get 4. 4 times 4 is 16. Okay, so we get 64 and 16. Okay, hopefully I haven't lost anyone. It's pretty simple. We can do 30 together. So 30, okay, you're going to take 30 and you're going to subtract it by the mean, which we found to be 31. So 30 minus 31 is -1. Now you're going to take the square root of that. Now you're going to take the, not the square root, you're going to go ahead and square it. So it's -1 times -1, which we know is going to go ahead and be 1. So now we have 64, 16, 1 plus 35. So now we get 35. Okay, 35 minus 31 is going to be 4. 4 times 4 is 16. Perfect. And let's get the last one, which was 40. So now we get 40. 40 minus 31 is equal to 9. 9 times 9 should be 81. So if we did our math right, we have 64 plus 16 plus 1 plus 16 plus 81 is going to be 178. We're going to divide that by 5. Okay, we get 35.6. Okay, remember that number, 35.6, because now we're going to take the square root of that. And where's my square root button? Is it this one? And that is 35.6. Okay, let's get the square root of what? There we go. So it looks like the standard deviation, the SD, is 5.96. Okay, so that's the standard deviation. I don't know if that's high or low, but nonetheless, let's type in that number. 5.96 is that the SD. All right, let's see what we got. Let's walk this through step by step. Verify your data. Damn it, ChatGPT. I was looking for a yes or no. Why couldn't you give me a binomial distribution of the answer that I was looking for? Huh? Okay, guys. So this is the math explaining it. I kind of verbally explained it. Variance, good. Standard deviation. So they give us the standard deviation of 5.97. I got 5.96. In the world of the lottery, baby, 7 is not 6. You are not a winner. Oh man. But nonetheless, yeah. Okay. So you're basically, so you were really close to standard deviation is approximately okay. So hey, we figured something out today. We figured out how to go ahead and get the standard deviation, which is nice. Now here's the thing. Let's go back to the 100 notes we have. I think it was this one. Okay, looking at this. Okay, so this was Joseph Granville. Number distribution was not truly random. So he's saying, hey, the number distribution, there's something in here, right? Let's ask ChatGPT the question most people are going to ask. Mind you guys, if you can't tell by now, I'm definitely taking a different approach. I'm not just asking ChatGPT, hey ChatGPT, give me the lottery numbers. Which actually, let's just do it for right now. Hey ChatGPT, let's play a game. Let's play a game. Give me the 5 numbers and the Powerball for the Powerball lottery. Lottery. I wonder what happens if I just do that. All right, let's play. Let's play. Here are your five numbers and Powerball numbers. Five numbers: 7, 14, 22, 33, 48. Powerball 12. Hey, I mean, ChatGPT. Hey, listen. If you literally wanted to ask ChatGPT for the numbers, it literally does give it to you. Which is pretty cool. Um, you know what? Let's for getting back to this. So this was today. Today's Tuesday. I know that the Powerball is going to be played tomorrow, so we're going to check the numbers. So and here's the cool thing about just being able to do this. It's just shits and giggles. So for that, we're going to call SNH. No, SNG. SNG. We asked ChatGPT. We asked Chat. We're not going to play these numbers, guys, but hey, we'll compare them. We asked ChatGPT for lotto numbers, lottery numbers, and they gave us 7, 14, 22, 33, 48, and 12. Powerball, we'll make a note like this, 12. Okay, we'll see if that hits, and we'll check in. And this was on what? This was today. What's the date today? This is 2/11/25. All right, cool. All right, guys. So we have that here. I want to ask ChatGPT. Hey ChatGPT. Hey ChatGPT. Based on okay, is there anything else? Hold on. Before we get into this, because I want to ask a few more questions before we head out. Uh, is there anything else in regards to number distribution? Is there anything else in regards to number distribution? Or were the concepts you told me good enough? I feel like there's more though. I feel like you're holding back on me, ChatGPT. You're right. There's definitely more to number distribution and the concept, and the concepts I shared are just a foundational start. Let's dive in a bit deeper into a few more related ideas that can enhance your understanding. Probability distribution. Hmm. Hmm. And welcome to the world of oh wow, this is a central limit theorem. What the heck? Okay, guys, we're definitely getting into some. All right, let's let's go and learn. Okay, so basically, what they gave us before was with regards to calculating standard deviations and the idea of normal distribution. That was like elementary stuff compared to just like skimming what I read. Probability distribution. A probability distribution shows how the probabilities are distributed over different values. It can be thought of as a map of likely outcomes. Discrete probability distribution. This applies to scenarios where the outcomes are distinct and countable. Okay, our situation is honestly discrete. We only have 1 through 69. There's only 1 through 1 out of 300 million chances. For example, when rolling a fair die, the probability distribution of each number 1 through 6 is equal. Okay, continuous probability distribution. This applies to data that can take any value within a given range, like height, weight, or temperature. A normal distribution bell curve is a key example of a continuous distribution. And but why is it called distribution? I mean, Wouldn't your height? Seems like height would be a little bit more. This applies to data that can take any value within a given range. Any value within a given range compared to distinct and countable. I don't know, dude. Okay. If you guys are good at math, or if you guys can figure this out, this kind of confuses me. Continuous probability distribution. How can your height and weight? I mean, that seems deterministic to me. That seems like it's discrete. Like, what's your height? Okay, my height is 6'5". Okay, what's your weight? 220 pounds. Okay, and that sounds weird. This applies to data that can take any value within a given range. Yeah, okay. I mean, I'm already struggling with the probability distribution. I'm thinking we're dealing with the discrete probability distribution because we're just looking at numbers and there's an exact number, so to speak, that's expected to come out. Okay, but let's continue. Types of distributions. Okay, this we already kind of talked about. Normal distribution, that's the bell curve. Uniform distribution, that was every outcome is equally likely, which that kind of goes ahead and I mean, I feel like these intersect with regards to uniform distribution. Exponential distribution, often used to model time until an event occurs, e.g., the time between arrival. Uh, I mean, that doesn't even make sense. Often used to model time until an event occurs, e.g., the time between arrivals at the bus stop. How's that exponential? Okay. Uh, Poisson distribution used for counting events that happen randomly and independently over a fixed interval. The number of cars passing through a toll booth in an hour. Wow. Okay. So we definitely know that there's. I mean, I did ask for more in-depth concepts. Guess this is what I get. Z scores. A Z score is a way to measure how far a data point is from the mean, expressed in terms of standard deviations. It tells you whether a value is above or below the mean and how many standard deviations. Okay. If that is unusually high or low. I think with the Z score is it's to figure out whether or not it's significant. And that's honestly something that I would want to look more into. These types of distributions, I guess they just explain the situation. Z score is, I'm leaning a little bit more towards learning about Z score. Central limit theorem. The central limit theorem is a fundamental concept in statistics. Well, I haven't taken statistics, so this is the first time I find this theorem out. It states that regardless of the shape of the original distribution of data, the sampling distribution of the sample mean will approach a normal distribution as the sample size increases, typically 30 or more. Ooh. The way I read that is you're going to need more than 30 samples of the numbers with regards to the lottery numbers. This means for large enough sample sizes, even if the data isn't normally distributed, the average of those samples will follow a normal distribution. And what type of distribution? Well, normal distribution in itself is the definition, which is what, a bell curve? Okay, I think we got something right. Um, as the sample sizes increase, okay, this is important in statistics because it allows us to make inferences and apply statistical methods even if we don't have a perfectly normal. So I guess the central limit theorem is just saying, hey, even if you take a small sample of the large sample, after having so many certain samples, you're going to start to see a normal type of distribution. So it's basically saying, like, hey, if you have one dot, it's kind of hard to see the pattern, but the more and more dots that you have, even if you only have 50 dots to give and you get 10 dots, so to speak, in this case 30 or more, you're going to start to see some type of distribution. I mean, that's pretty simple. It's not as, this isn't as complicated as I thought. I think so. Skewness and kurtosis. Skewness refers to the degree of asymmetry of a distribution. If the distribution is skewed to the right, positive skew, we literally just learned that not too long ago. I think positive skew was if it has more negative numbers compared to positive numbers. Okay, it means most data points are smaller with the tail to the larger values. Okay, yeah, that's literally kind of what we said. If it's a skewed to the left negative, most data points are larger with the tail. Okay, skewness. So I mean, we learned something new. Kurtosis measures the tailedness of a distribution. High kurtosis means more extreme values, outliers, and low kurtosis means fewer extreme values. Okay, I can mess with that. I can definitely comprehend that. I like this. I actually really like this because I want to compare it. I want to go ahead and make a note of that. Let's go ahead and see. Let's go back over here. So this was just a side note. Side note. All right, that's just a side note. But let's go ahead and put this here with skewness, okay? Because we talk about skewed distribution. Let's go ahead and talk about. We're learning some more mathematical terms. Yay! Honestly, I feel like this is a way they should teach math. At least another way to teach math. With regards to, hey, I want you to try to solve this problem and let me know what keys and concepts and processes you come up with. You know, measures, especially with something with like ChatGPT. Um, and this is it basically measures outliers. Measures more extreme values, outliers, and low means okay. So high means more extreme values. High means more outliers. Low means less outliers. Um, let's go back. Where'd it go? Okay, so kurtosis. So high equals more outliers. Low equals less outliers. Yeah, that's exactly what it basically is. And I'm pretty sure you guys can you guys we can measure this. I mean, you can say it verbally. You can say it. I forget what they say when you measure. Not when you measure, but when you go ahead and what is wait? What's the thing I'm looking for? I'm looking for. Oh, come to me. Empirical rule. Okay, what's this empirical rule? Empirical rule 68 through 95 through 99.7 rule. I have no idea what that means. Okay, but for a normal distribution, about 68% of the data falls within one standard deviation of the mean. Ooh, about 95% falls within two standard deviations, and about 99.9%, 99.7% falls within three standard deviations. This rule is helpful for understanding how spread out your data is and can help make quick predictions about the range of data. Explain. Okay, so far we have the empirical rule. We already talked about this. Central limit theorem. That's more of a concept than more than mathematical. It's just the idea, and then the z-scores. So when it comes to what it would basically be, so things to review would be okay, would be z-scores. And it would also be, I mean, we'll put CTL. I mean, that's an important concept. Central limit theorem. More of a concept. More of a concept. 30 plus samples or more. Okay. And empirical rule. Empirical rule. 68, 95, 99.7. Here's the thing, guys. What I still don't comprehend is what do they mean by what is it? Because when we, explain to me the idea of one standard deviation, two standard deviations, three standard deviations. Okay, because I mean, we literally in this video we calculated the standard deviation, but what do you mean by okay? Explain to me. I want to know more. I want to know more about the empirical rule, and I want to know about more about the z-scores. I think the z-score. I think the z-score is literally like one standard deviation, two standard deviations, three standard deviations. And this is saying the empirical rule saying that, hey, 68% of your data is going to fall within the one standard deviation. 95% of your data is going to fall within the second standard deviation. But I want to go ahead, explain to me the empirical rule, please. Yeah, just explain it to me because I don't get that. I want to know what you mean by standard deviations. Absolutely. Let's dive into the empirical rule, also known as the 68, 95, 99.7. This is a key concept that applies to normal distributions, so bell-shaped curves. Here's the thing, though. We don't normal distribution. This is where things can, if we haven't already messed up, this is something where we can really mess up because the bell-shaped curve. So this is the empirical rule only applies to the normal distribution. But what did we already learn? We learned that there's actually more than there's more ways. There's many distributions. You have your normal distribution, you have your uniform distribution, you have your exponential distribution, you have your Poisson distribution. I wonder, okay, we're going to ask this question. Okay, based on the 1, 2, 3, 4, based on the 4 distributions, which one does the Powerball lottery use? I mean, I'm pretty sure we can take the numbers and then go ahead and get and try to transform it into a normal distribution, and then we can go ahead and try to imply the empirical rule. But if the lottery in and of itself is not, if its identity isn't truly a normal distribution, then applying the empirical rule, I mean, I don't think it would have any validity to it. I would think. I don't know. I'm not sure. Mind you, this is only our 3rd video. But going back to this, explain to me the empirical rule, please. So it was saying that the empirical rule applies only to a normal distribution, bell-shaped curves, which are very common in statistics, especially for things like test scores, heights, and many other natural phenomena. Well, I mean, trying to win a lottery, is that a natural phenomena? The empirical rule states that for normal distribution, visualizing 68% within one standard deviation. If you draw a line, one standard deviation to the right of the mean and one standard deviation about 68 will fall between. Okay, that makes sense. A simple example. Let's say you have a data set representing the heights of students. Okay. The mean height. Okay, standard deviation. Yeah, I mean, that kind of makes sense. So our previous standard deviation with the numbers that we had was 5.96. So it's saying you're going to go ahead and take you're going to take the exact, I guess the not the median, but the mean of the bell curve. You're going to get to the very tip of the bell curve, and from the tip of the bell curve just draw a straight line, and then you're going to find your standard deviation, which would be 5.96 to the left, 5.96 to the right. And then from there, you're going to add another 5.96 to the left, another 5.96 to the right. And then for your third, you'll add another 5.96 to the left and to the right. That makes more sense. But once again, this is only in what would be a normal distribution, which we come to the question and we'll end it with this. Okay. Based on the 4 distributions, which one does the Powerball lottery use? Dude, if it says normal distribution, guys, I'm gonna get I'm gonna get pretty excited. Okay. If you've been following along this far, you know the implications, right? Because now we're literally looking at the number distribution. We can literally look at tangible data. Okay, so let's go ahead and do this. Based on the forward distribution, which one does the Powerball lottery use? Boom. Come on, ChatGPT. Normal distribution. Normal distribution. Oh, gosh. Gosh, of course. Of course. Uses a uniform distribution for the selection of its winning numbers. Here's why. In a uniform distribution, each outcome has an equal chance of occurring. In the case of the Powerball, 5 numbers are drawn from a set of 69, ranging from 1 to 69, and each of those 69 numbers has an equal chance of being selected. Um, why not other distributions? Normal distribution. This is a bell-shaped curve where most of the values are clustered around the mean with fewer values. Okay. Skewed distribution, binomial distribution, recap, Powerball. Okay. What if we take? I want to ask ChatGPT. What if we take? Of course, it wasn't going to be that easy. What if we take the Cal lottery numbers? Cal lottery numbers. Or I mean, how could you even turn it into a normal distribution? Can you take the outcomes of lottery number winnings and turn it into a normal? How would you turn it into a normal distribution? Normal distribution? Is that possible? All right. Let's see if that's possible. Because I mean, if we can't do that, guys, then basically, oh yes, theoretically possible to take the outcomes of the lottery number and transfer them into normal distribution. But there are important considerations and steps involved. Let's break it down. Lottery outcomes are discrete. Powerball is a discrete event where you're selecting a specific set of numbers. In normal distribution, data is continuous, like measurements of heights, weights, and temperatures, and follows a bell curve. However, lottery numbers are finite and only take on specific values. I'm still having a hard time between those that concept, continuous and discrete. Like I don't like that doesn't make sense to me. How is my height continuous? Like what exactly about measuring height is continuous? I think that your height would be a specific number, and I get it. Like sometimes like hey, you're not the same height as you were when you're 10 compared to when you're 100, and you might have a various degree, but I mean at a certain point, like whether you measure when you're 5 or whether you measure when you're 10 or whether you measure when you're 100, you have yeah, that's I might need to look that up on my own, guys, because I want to focus on learning some of the math on this end, but I'm definitely stuck on that. Discrete events like drawing numbers don't directly form a normal distribution. Well, maybe you need 30 or more samples. To transform or approximate the lottery outcomes into a normal distribution, you could simulate a large number of lottery draws. If you simulate many draws of the lottery over a long period of time, say